my face because there is the case that no one will see my face behind the mask. So yeah. In the program, I have a large name, Emmanouil Vlatakis. This is a typical problem that I have. My real name is Manolis, and my research interest lies on the intersection of theoretical computer science, game theory, machine learning, and optimization. Actually, just because we're in meeting conference, I decided to say, who am I? So I was born in Athens. I did my undergrad studies in the only school that we're doing that stuff, in NTUA. And right now I'm graduating from Columbia University. I can say that my dissertation is about noise in total search problems, but I decided a little bit to start with a story. I know that we have heard lots of stories today, and I want to do something more relaxing. So I have a question for you. Do you believe that this is a real polyhedron? Hans, quickly. Do you believe that this is real, yes or no? Okay, I have one. All the others believe that it is not real. Okay. So in geometry, Norman Johnson, in 1966, proposed the following construction. He said, okay, I will call a Johnson polyhedron to be a strictly convex polyhedron where each face would include only regular polygons. And actually, he presented a list of 92 polygons, 92 polyhedrons that they cover this assumption, plus all the ancient mathematician prisms that they cover also that assumption. Now, again, I will ask that question: is that the polyhedron a real polyhedron, a real convex polyhedron? It seems so, right? So the answer is no. 3 years later, Soviet mathematician Zalgaler proves that the list of Johnson with the 92 polygons was complete. So that means that this structure cannot exist, which does not make sense because the photo is real. So something has happened. And of course, the reality is that, just to explain my modus vivendi here, is the reality is that the theory speaks always about worst case analysis. The worst case analysis here is that we have perfect guarantee, for example, about the measurements. But if I ask you and I challenge that with probability 1, if you go at home and you do that experiment, you will achieve with probability 1 to construct a polygon, for example, with hexagons and pentagons, that it is forbidden by Zalgaler proof. And the reason is the near misses that we have in the measurements. So this is my question in my research. So that is the way that I started working in local optimization. And actually, my first work was about the smooth complexity, a way to go beyond the worst case analysis. Typically, for the majority problems that we have in local optimization, they are NP hard, PLS complete, exponential worst guarantees. So no one would like to solve them, but there are prominent solutions that they are actually local heuristics, and there are ways in theory to prove that they are really good enough. Actually, if you think about it, in the previous century, we're applying, from the previous century until now, we're applying just one algorithm that is a local search method, and we call it gradient descent. And like this is my first paper, I think, as a PhD, we proved that even without gradients, if the stuff are really smooth, you can avoid saddle points and have some good local solution. But if we ask ourselves nowadays, I think in bootcamp of learning games, we establish it really nicely with many different ways that optimization is not something so simple. For example, we have to get into data that they are shared in multiple different servers. We have to do some federated situation where we want to learn different stuff from different learners. And like the bots in the warehouses have to connect each other very, very locally. So actually, yeah, this is the whole point of my research, that is what we're doing today. That is that hopefully we'll do in the future. And yes, I think that it is ubiquitous that games exist totally in optimization in many different fields. So yeah, in the majority of the problems that I have worked was about the min-max optimization, and especially how we use them for typical tricks that we have for the generative adversarial networks. where I try to prove again, like what I said, I want to make, I'm trying to meet you. I'm trying to say what I am interested in. And this is what I am interested in, to understand mathematically what are the phenomena that I see. So if I see the cycles, I want to be able to prove the cycles. This is one of these two works aim exactly on that, to understand different kind of models of non-convex, non-concave optimization that they are applied in practice, like in GANs, to prove that we have such kind of phenomena. And after that, we started to discuss about the multi-agent setting, and when players are playing stuff like no regret dynamics that many other speakers had discussed today. So I avoid the definitions, and I just pass to the main message. So the main message that we had in our research, I think that you can see it very clearly in that picture, that typically if you follow a no regret dynamics, this is a totally rational assumption. What we have is convergence to strict equilibrium, but for a mixed NAS equilibrium, the only thing that we can do is to discover the phase of the equilibrium. But what we cannot do is really to converge to that point. Now I will hear the correct note that, look, we had invented some machinery to converge to that points with different dynamics, but all of them again breaks when, and this is also in some of our results, if you put some stochasticity inside. So all of these models, if the payoff that we are getting has again some noise, they have this kind of, all of them, I mean, this is a bad word, the totality shouldn't be a word of a scientist, but you understand my meaning. The majority of them, they will behave like that. So just to follow now the abstract that I gave, something that had made me really interested nowadays is what a model that we present with Ioannis Panagias and Phibos Kalogiannis. This is really inspired by what is happening in practice. We call them, there is actually a long literature in that problem. It is one problem that I would like to work in Simons, and we call them team games. So a two-team game is the following: you have your players, you separate them into different teams, and every player has some actions. And now, how we will make econometrically the game to be two-team game? The solution is easy. Every player that belongs in one team will share the same utility with the co-members of the team. Now, if you want to have two-team zero-sum games, those utilities will sum up to zero. There are lots of different applications. I will stay in the second one because Phibos, my co-author and my advisee in NTUA, really like that. One example is actually the, all this Reddit, Wall Street short bidding that happened last year with GameStop, where you have two teams that they're trying to collaborate, but at the same time they have their own incentives to play differently. So that is the reason that we really would like to understand that kind of games. So the first question is how hard is to compute an NAS equilibrium in a two-team zero-sum game. The best answer that we had right now is that they are CLS hard. And I put that because approximating an epsilon NAS equilibrium in a congestion game is a CLS. So what I found even more interesting about this kind of games is that all of the classical discretization that we know, like gradient descent, optimistic gradient descent, extrude gradient, optimistic manipulative updates, everything that we know, they actually cycle around in that phenomenon. So in order to solve that solution, we proposed a new method. It is a new method of discretization that actually was proposed by people that they are doing feedback control theory. Actually, we found out that there is a similar washout filter with the discretization scheme that we did that is used in aviation for the Dutch roll movement. So yeah, this is the method, but I don't want really to be more tiring than what I am right now. So we achieved to show some sufficient solutions, but we strongly believe that there is something more interesting in that kind of feedback control discretization that has not been yet utilized by the optimization people. And I would be really interested in looking on that. In general, this is my perspective. This is my research agenda. I would like to be member of that kind of world where I'm trying to create theory about the real machine learning. I'm trying not to create theory that does not speak about what is happening in practice. And at the same time, always remember that. And just for a thinking slide, another problem that is a very game theoretic problem that I am trying to solve is the following problem. It belongs to the tragedy of commons interpretation. So I'm trying to solve the reading group assignment. I want to incentivize the Simons participants with a mechanism without money to present some interesting work in our equilibrium and computation reading group every Tuesday, 11 to... I always make a mistake about the noon, if it is AM or PM, but you got my point. You're really invited to come. Thank you very much. Someone else.
Could you comment a bit on the CLS completeness as well?
Oh, yeah. Yeah. Sorry, can you repeat? Oh, what is the result?
Yes.
What is the result that we have? Okay. What we can really prove is actually that if you give us the potential, you can put it. If I have the potential of the. Yeah, I have to clarify that we have not achieved to find the membership of the problem. We have only the hardness of the problem. So yeah, I should clarify. Thank you for the question. So the only thing that we can say is that if you give me a potential gain, then I can put the potential function in the utility. I can create a dummy. This is actually the reduction. I can create a dummy team gain. And the result, it is carte blanche, the result of the team zero-sum game will give me the epsilon mixed Nash of that problem. But I was planning to ask also you what we can show about the, to understand a little bit the membership of that kind of problem. Yeah, thank you for the question.
So that's thanks for that presentation for two-team problems. So
this is correct. This is correct. There is duality gap. There is a paper from Vazirani and Schumann that proved that actually different asymptotics about that. So in that case, what is the meaningful equilibrium? This is a very good question. The reason that we decided to track Nash equilibria is that for all the other cases, there are actually results that they say that they are intractable under some complexity sense. So that is the reason that first of all I said, okay, let's look on that. Of course, always there is like the min-max where I will look only one, the preference in one thing, but I thought that this is an unfair situation. I try to be like fair in both of the two teams and understand an equilibrium that would be fair to that. Yeah, there is an interesting question that also we're trying to address a little bit with Ioannis. If there is no duality gap, is the case if I come structurally and I have the only assumption that there is no duality gap, can we prove that at that case we will discover Nash equilibria? This is not clear in comparison with the classical two-player zero-sum game, but it would be interesting to discuss about that and see what is happening. Thank you very, very much.